Okay, so as promised, I said I would make a little video with a proof of Euler's formula, and then I'll make another little video with a proof that there are only exactly 5 regular polyhedron, or platonic solids, if you've ever heard that term. If you want to Google that, that'd be great. So remember, Euler's formula is supposed to be for planar graphs, and Euler's formula says that the vertices minus the edges plus the faces is always equal to 2 for a planar graph. And so the proof of it is actually quite easy. You can do it by induction. I won't do a formal induction, but I'll just call this an informal induction. So just like a formal induction, we need a base case. And I'm going to do the silliest possible base case. Oh, and by the way, before I do the base case, let me say I'm going to do an informal induction proof. And I'm going to, I'll induct on the number of edges. And you'll see where that comes out important. But we'll do the base case first. And that is, we'll do a couple of base cases actually, but the first base case is we have a connected graph with exactly one vertex. So one vertex. No edges, and then one face. Here's a picture of that graph. It's a vertex, and the face is everything around it. Of course, vertices minus edges plus faces, vertices minus edges plus faces is has to be equal to 2 for Euler's formula to follow. Of course, there's one vertex, 0 edges, one face. That's 2. Now this is the trivial case. How about one edge? Now I claim there's only one graph with one edge, and it looks like this. It's a single edge with 2 vertices, one edge, and then the face, which is the thing surrounding it, sort of trivially, there's one face. So sort of, I don't know how to indicate the face, but this face is the plane on which it lies. So we have vertices plus edges minus faces is equal to, well, there's 2 vertices. Oops, and I said minus edges plus faces, but I wrote minus faces plus edges. There's 2 vertices. There's one edge, and one face. So that's 2 minus 1 plus 1 is 2, so check. Should have a check mark there. And this actually, this proof kind of, this actual one edge example sort of, in a way, shows why it's true. But you'll see more here in a second. So I'm going to induct on the number of edges, so my inductive hypothesis, or my inductive, actually I should really call this my inductive assumption. Well, I'll just call that IA, is that for any connected planar graph the vertices minus the edges, any connected planar graph with n edges, vertices minus edges plus faces is equal to 2. So in other words, I did it for a graph with 0 edges, I did it for a graph with 1 edge. That's my sort of my base cases. The 0 edges is really my base case, but I did one more example. And then we're going to assume for any graph with n edges, this holds. And we're going to show that this implies that it's true for n plus 1, for any graph with n plus 1 edges. And there's two cases. So notice that a graph with n plus 1 edges can be built from a graph with n edges in exactly two different ways. Firstly, a graph with n edges can be built to a graph with n plus 1 edges. So this is a sort of n edge planar graph. The first way to build one is to take one of the vertices and add an edge to it. But if I add an edge, I'll have to add a vertex on the end of it. So then I have, now I've created a graph with n plus 1 edges. So this is the n plus first edge. Then how do the vertices change? Well, there's the vertices from the n-edged graph plus 1 minus the edges from the n-edge graph, but I've added one more edge. So there's one more vertex, one more edge. And the number of faces doesn't change because this thing doesn't create a face. And so I know that the vertices plus edges minus faces equals 2. I've added 1 to the vertex and 1 to the edges, so that's v plus 1 e minus 1 plus f equals 2. I should have put a question mark above there. So vertices minus edges plus faces is equal to 2 by assumption. So the other case is that however our graph is drawn, our new edge connects two existing vertices. So somehow this graph, however, it's got, maybe hundreds of edges, but we connect. So we connects two vertices on the graph. So this is, again, this is my n plus first edge. Well, what happens if I connect two vertices on an existing planar graph? It creates a new face. Now, like I say, this is an informal proof, so you should convince yourselves of these facts. But what does that mean? That means the number of vertices didn't change. The number of edges didn't change. Or the number of edges did change. We added one edge. I'm sorry. The number of faces did change because I've added Darn it, I put the minus in there in the wrong spot again. Keep doing that. So I've got minus here, plus here. I've added one face and one edge. Of course, this reduces to, well, I've got vertices minus edges minus 1 plus faces plus 1. Those cancel, so I get vertices minus edges plus faces, which by assumption was 2. So adding a new edge to an already existing planar graph doesn't change the sum, the vertices minus edges plus faces. So this implies vertices minus edges plus faces equals 2 for all planar graphs. This is a little bit of a subtle proof, so you should review it, and I can slowly pan through it if you need me to. But we did a base case. We inducted on the number of edges, and we showed that any way of adding an edge doesn't change the sum, vertices minus edges plus faces. So there's another little subtlety here. You'll notice that we tend to use, if you look in the homework and in the examples in the book, we tend to use this to show a graph can't be planar. But we don't use it to show a graph can be planar. And that's because it's a one-way implication, which is any planar graph. So notice any planar graph satisfies vertices minus edges plus faces is equal to 2. But non-planar graphs can also satisfy vertices minus edges plus faces is equal to 2. So in other words, if your graph can't satisfy this, it can't be planar, but it doesn't go the other way around. You can't prove something is planar by finding the vertices minus edges plus faces is equal to 2. So that's why we usually prove something can't be, often can establish something can't be planar, but it's much harder actually to establish that something is planar. Anyway, I'll leave that off, and I'll try and do a quick video also of the fact that there are exactly 5 Platonic solids.